So what exactly is a transformation? As mentioned previously, vectors are used to describe, among other things, directions and positions in 3D space. For instance, the position of the vertices of your 3D triangles are stored in vectors, as are their colors and surface normals. However, these positions are unlikely to remain static throughout their lives in your graphics applications. Your 3D objects will move, grow, shrink, and turn within a scene. More formally, displacement is known as translation, growing and shrinking as scaling, and turning as rotation. Such operations are known as transformations. Furthermore, in order to display your object to the screen, they will be considered from multiple frames of references, coordinate systems. You'll use matrices to transform positions and directions from one coordinate system to another, and to apply translation, scaling, and rotation. Before diving into the specific transformation matrices, it's important to note that we'll be using homogeneous coordinates. This coordinate system allows you to incorporate translation to a 4x4 matrix along with scaling and rotation. Matrix multiplication is associative, therefore a single 4x4 matrix can encapsulate all of these transformations. With homogeneous coordinates, each position has 4 components, x, y, z, and w. The x, y, z coordinates are the normal 3D coordinates. The w component has the value 1 for position and 0 for directions. As you'll see, that w equals 0 for direction vectors nullifies translation, and this makes sense because direction vectors have no location in 3D space. To transform a vector, you perform a vector to matrix multiplication, which is just a matrix multiplication against a row vector or a column vector. By way of example, on the screen you'll see the 3D scaling matrix. The values along the main diagonal represent the scaling vectors for the x, y, and z axes. If these values are the same, the vector will be scaled uniformly. Note that the similarity to the identity matrix, which is merely a scaling matrix with 1s along the diagonal. Here is an example of transforming a position vector by a non-uniform scaling matrix. The position stored in A is -4, 2, and 6. The 4th row, w component with a value 1, is necessary because the scaling matrix has 4 columns. The act of translation moves an object along the x, y, and z axes. The translation matrix is defined with x, y, and z displacement values along the 4th column. Here's an example of translating a position vector 10 units along the x-axis, 5 units along the y-axis, and 6 units along the negative z-axis. But note that if the w component of the vector was 0, as if the vector represented a direction, the transformation would have no impact. Rotation is a bit more complicated because there is a different rotation matrix for each axis. If this looks a bit scary, don't stress. The GLM math library has functions for creating each of these rotation matrices. But as you can see, rotation around the x-axis has a cosine and sine, negative sine, and cosine smack dab in the middle of our 4x4 matrix. And this varies for the y and z axes. Here's an example of rotating the position 100, 90 degrees, which is pi over 2 radians, clockwise around the z-axis. So notice that the 1001 row vector is multiplied by the rotation vector around the z-axis for pi over 2, for cosine of pi over 2 is the value 0, sine of pi over 2 is the value 1, and then negative pi over 2, sine pi over 2 is negative 1, and of course cosine of pi over 2 is still 0. When we do that multiplication, the result is 0, negative 1, 0, 0. So we've just rotated that position, if you will, longitudinally, clockwise around the z-axis. Instead of applying each of these transforms individually, they can be concatenated into a single transformation matrix. For example, a scale, rotation, and translation matrix can be combined as w equals t times r times s. Transforming a position vector by this concatenated matrix would scale, rotate, and translate the vector in a single operation. However, the order of concatenation is important. Concatenation is performed from right to left, and matrix multiplication is not commutative. So for example, suppose you were rendering the Earth orbiting around the Sun. It has both translation away from the Sun and a rotation around it, and the concatenation should be performed in that order. However, if you also wish to simulate the Earth's axial rotation, you'd want to perform that rotation before the orbit transformations. In this scenario, the complete concatenation matrix would appear as the world W equals rotation for the orbit times the translation times the rotation axial. You can concatenate any number of individual transforms. Just be aware of the right to left ordering. In addition to scaling, translation, and rotation, you can use transformation matrices to move a vector from one coordinate system to another. Typically, your 3D models will be created in a digital content creation package, Autodesk Maya or 3D Studio Max, for example. And a model will be authored in its own coordinate system called object space or model space. Your scenes may contain hundreds of individual models, but these objects are rarely authored as a whole. Rather, each object is stored in a separate file, and its vertices are relative to its own origin, with no inherent relationship to another 3D model. In order for these objects to interact, they must share a common coordinate system. They must exist in the same world, and therefore must be transformed from object space to world space. A world transformation matrix, or world matrix, is made from concatenated scale, translation, and rotation matrices. To apply the world matrix to a 3D model is to multiply each vertex in the object by the matrix. From world space, the object is then transformed into view space, a coordinate system relative to a virtual camera. The properties of the camera define a volume within which the objects are visible. This volume is known as the view frustum, and it can be visualized as a pyramid with the top chopped off. A view matrix is used to transform vectors from world space to view space, and is commonly created through a combination of the camera's position in world space, a vector describing where the camera is looking, and a vector describing which way is up. You'll use the GLM math library to create a view matrix in Lesson 3. Object space, world space, and view space are all three-dimensional coordinate systems. However, computer screens are two-dimensional, and it's the projection matrix that projects this 3D geometry onto a 2D display. It's in this stage that the illusion of depth is created, where, for example, objects that are closer to the screen will appear larger than those that are farther away. This is known as perspective projection, as opposed to orthographic projection, where all objects appear to be the same distance away from the camera, irrespective of their actual positions. The properties of the projection matrix help define the view frustum and include a near plane, a far plane, a vertical field of view, and an aspect ratio. Objects between the camera's position and the near plane are not rendered, nor are objects past the far plane. A good analogy here is the tip of your nose, which is the near plane, and the horizon, the far plane. The field of view defines the extent of the frustum, and the aspect ratio is typically the width of the display, or window, divided by the height. As with a view matrix, the projection matrix is commonly constructed through GLM API calls. The transformations for a world, view, and projection space are typically performed within the vertex shader, and you are responsible for them. You can apply each transformation individually, or you can concatenate the three matrices in what is commonly referred to as the World View Projection Matrix, or WVP. Once multiplied by the projection matrix, the coordinates are in projection space, also known as homogeneous clip space. This concludes Lesson 2.3 and our discussion of 3D mathematics, and hopefully you found that it wasn't so bad after all. In the next lesson, we'll continue writing OpenGL applications.